Dear students, in the last class we have discussed some examples for metrics defined on different sets, and also we have discussed some inequalities known as Holder's and Minkowski's inequalities. So with the help of these inequalities we will see some more examples for metrics defined on different sets. So let's consider this example. For 1 less than p less than infinity and xy belongs to kn, we take our x as k power n. Now we define dpxy as like this, that is summation j varies from 1 to n mod x of j minus y of j power p whole raised to 1 by p. So with this definition we want to show that this dpxy is a metric on this kn. Okay, so for proving we will use uh, the inequalities which we already discussed in the last class. Okay, here we want to show that dpxy which is equal to summation j varies from 1 to n mod x of j minus y of j power p whole raised to 1 by p. This is a metric on kn. Okay, so for the first condition, here given dp of xy equal to summation of modulus of this x of j minus y of j. Okay, so this means we have clearly dp of xy is greater than or equal to 0. Okay, the first condition is very clear. Also, if dp xy equal to 0, so this means summation j varies from 1 to n mod of x of j minus y of j power p whole raised to 1 by p which is equal to 0. So this means modulus x of j minus y of j power p which is equal to 0. So this means this is equal to 0 for all j. Okay, so this means x of j equal to y of j for all j. So this means x is equal to y. So if dp of xy equal to 0, if and only if x equal to y, so our first condition is satisfied. Now let's look at the second condition. We have dp of xy equal to, by definition, summation j varies from 1 to n mod x of j minus y of j power p whole raised to 1 by p. So this can be written as summation j varies from 1 to n. We reorder this, so this is equal to y of j minus x of j, okay, modulus y of j minus x of j power p whole raised to 1 by p. We can write like this because here this is modulus. So this is equal to dp yx. Okay, so dp of xy equal to dp of yx. So the symmetry is also verified. Now for the third condition, we take x, y and z from kn. Okay, then we have dp of xy which is equal to, by definition, summation j varies from 1 to n mod x of j minus y of j power p, whole raised to 1 by p. Okay, so this is equal to summation j varies from 1 to n mod x of j. We subtract and add z of j. So minus z of j plus z of j minus y of j power p whole raised to 1 by p. Okay, so we know by Minkowski inequality says that for 1 less than or equal to p less than infinity, we have summation j varies from 1 to n mod aj plus bj power p whole raised to 1 by p, which is less than or equal to summation j varies from 1 to n mod aj power p whole raised to 1 by p plus summation j varies from 1 to n mod bj power p whole raised to 1 by p. We can split like this. Okay, so we use this inequality here. That means we can write this is less than or equal to, in Minkowski inequality we substitute aj as x of j minus z of j. Okay, and bj z of j minus y of j. Okay, so we have less than or equal to summation j varies from 1 to n. This is our aj. So summation by Minkowski inequality, summation j varies from 1 to n mod aj power p whole raised to 1 by p. Here our aj is this one. Okay, so this is mod x of j minus z of j power p whole raised to 1 by p. Okay, plus summation j varies from 1 to n mod z of j minus y of j power p whole raised to 1 by p. Okay, so what is this? By definition, this is equal to dpxz, and this is dpzy. Okay, so the third condition, that means triangle inequality, is also verified. So from here we can conclude that dpxy defined like this is a metric on Kn. Okay, here we can notice that if n equal to 1, okay, that means our x is equal to k, then all the metric dp were 1 less than or equal to p less than or equal to infinity, reduce the usual metric given by dxy equal to mod x minus y for xy belongs to k. For x is equal to kn, here we have this summation j varies from 1 to n. If we take n equal to 1, then here only x minus y. Okay, there is no summation. So this is mod x minus y power p whole raised to 1 by p. So this is actually mod x minus y. So this is our usual metric. Okay, so if n equal to 1, then all metrics dp were 1 less than or equal to p less than or equal to infinity, reduced to the usual metric given by dxy equal to mod xy for xy belongs to k. Now we generalize this consideration, that is, for 1 less than or equal to p less than infinity, consider the set of sequences in k, which is denoted as LP. So here our x is equal to LP. LP is defined as a set of all x1, x2, etc., such that x of j belongs to k, and summation j varies from 1 to n mod x of j power p less than infinity, which is finite. Okay, so here the elements in this LP is like this: x is equal to x of 1, x of 2, etc. Okay, so for x is equal to x of 1, x of 2, etc., and y equal to y of 1, y of 2, etc. in LP, we define dpxy as like this. summation j varies from 1 to infinity modulus x of j minus y of j power p whole raised to 1 by p. In the previous, our x was x is equal to kn. Okay, at that time our summation varies from 1 to n, considering only n tuples. Okay, now here we are considering sequences. So the elements in our x is x of 1, x of 2, etc., like this sequences. Okay, so that's why here we are defining like this, that is summation j varies from 1 to infinity mod x of j minus y of j power p whole raised to 1 by p. Okay, now we want to show that this dp of xy is also a metric on lp. Okay, so in order to prove, we will verify this dp of xy will satisfy all the axioms of metric. Okay, we let aj equal to x of j and bj equal to minus y of j. Okay, for j varies 1, 2, 3, etc., and letting n tend to infinity. Then by Minkowski inequality, we can write dp of xy less than infinity for all xy in LP. So first we want to show dp of xy greater than or equal to 0. It is clear from this definition. As we have discussed in the previous example, this is clearly dp of xy is greater than or equal to 0. Also, if dp of xy equal to 0 means mod x of j minus y of j equal to 0 for all j. So that means x of j equal to y of j. So this implies x equal to y. Okay, so dp of xy greater than or equal to 0, and if dp of xy equal to 0 means x is equal to y. Similarly, the second condition also we can easily verify, that is dp of xy equal to dp yx. Okay, now for the triangle inequality, that means the third condition, if we take any z from this LP, z is like this, z of 1, z of 2, etc., okay, which is in LP. Now we let aj equal to x of j minus z of j and bj equal to z of j minus y of j for j varies 1, 2, 3, etc., and letting n tend into infinity. Okay, in the same inequality. So by using this Minkowski inequality, we can show that dp of xy less than or equal to dp of xz plus dp zy. So please verify that this dp xy satisfies all the conditions of metric. Okay, so we can conclude that this dp is a metric on LP. Now our next example is set of all bounded sequences in K, which is denoted as L infinity. Okay, which is defined as set of all x of 1, x of 2, etc., such that x of j belongs to K and supremum j varies from 1, 2, 3, etc. Mod x of j is finite. Okay, here the elements in this set is like this, x of 1, x of 2, etc. So if we take any x and y from this L infinity, which are of the form x of 1, x of 2, etc., and y of 1, y of 2, etc., which is in L infinity, then if we define d infinity xy as supremum j varies from 1, 2, 3, etc., mod x of j minus y of j. Okay, then clearly we can verify that this d infinity xy is also a metric on L infinity. Okay, now our last example is b of t. Okay, which means set of all k valued bounded functions on T. Okay, here the metric space L infinity is a special case of this b of t. Okay, so b of t can be defined as set of all x is a function from T to K, such that supremum T belongs to T, mod x of t is finite. Okay, so if we take x and y from b of t and we define d infinity xy as supremum t belongs to T, mod x of t minus y of t, then we can easily show that this d infinity is a metric on b of t. So this metric is known as supremum metric. Okay.